The table of contents include learning outcomes. Second, introduction to the Ligand field theory, which basically tells you that why Ligand field theory came into being over the crystal field theory. Third is the delocalization approach to the bonding, that is the molecular orbital theory. Introduction to the molecular orbital theory, homonuclear diatomic molecule, principles of the Ligand field theory, NENT, molecular orbital theory of various octahedral complexes in general and for certain molecules. Ligand consideration consisting of the various kinds of ligands possible and how the sigma bonding takes place in the octahedral environment. Next, we'll discuss the molecular orbital diagram of various octahedral complexes. After learning this module, you will be able to know the basic principles involved in the formation of a molecular orbital diagram of the molecular orbital theory. We will learn the rules of drawing the molecular orbital diagrams, identify the ligands as the strong and the weak field one, depending upon which the various donor properties are related. We will evaluate the ligand field splitting parameter in terms of the ligand field strength. Now we'll introduce to the ligand field theory as to why it was introduced over the crystal field theory. The crystal field theory basically describes the bonding between the ligands and the central metal ion orbitals purely on the electrostatic basis. However, the interaction between them is generally stronger as compared to the accepted one. This is because in reality there is some amount of sharing of electrons between the orbitals, or the transfer of electrons from the metal to the ligand or from the ligand to the metal takes place. Also, the interactions should be treated in terms of bonding interactions instead. Hence, we can say that the most severe limitation of the crystal field theory is that it cannot accommodate or account for the fact that why the chemical bonding is taking place, since the complexes may also be formed by joining of the neutral atom with that of the neutral or cationic ligands. The ligand field theory builds up the interaction between metal and the ligands purely on the form of covalent bonds between the ligands and the metal. To do this, a molecular orbital approach must be taken into account. We'll be discussing delocalized approach to the bonding, which is basically your molecular orbital theory. Introduction to the molecular orbital theory includes the localized model for bonding, such as Lewis and valence bond theory, assumes that all the electrons are constrained in bonds between atoms or lone pairs. In contrast, the delocalized approach to bonding places the electrons in the molecular orbitals that cover the entire molecule instead of taking only the atoms or the lone pairs. In most of the cases, molecular orbital theory provides with a more precise picture of the electronic arrangement of the molecules, and it gives rise to more relevant information about their chemistry and reactivity. Molecular orbitals are constructed from the available atomic orbitals in the molecule such that the total number of molecular orbitals is equal to the total number of atomic orbitals combining them. Linear combination of atomic orbitals, which is the expanded form of LCAO, is important since it tells the total number of molecular orbitals formed will be equal to the total number of atomic orbitals combining them. In MO theory, the atomic orbitals will come from several or all the atoms in the molecule, and once we have constructed the MOs, we can build an MO diagram, which is an energy level diagram for the molecule, and fill the molecular orbitals with the electrons using the off-Bohr principle, according to which the electrons should be filled according to their increasing energy levels. some of the basic rules for writing the molecular orbital diagrams using the linear combination of atomic orbitals has been summarized as follows. The first rule says that the atomic orbitals must reduce or combine together to give the molecular orbitals, which should be equal in number. For example, if we are combining 6 atomic orbitals, it will be giving us 6 molecular orbitals. Second, to combine the atomic orbitals, they must be of appropriate symmetry. The third rule says that we have to combine the atomic orbitals according to their similarity in energy. That is, both of them should be somewhat similar in energy, not too low or not too high. Each molecular orbital must be normal and must be orthogonal to every other combining molecular orbital. Also, closer the atomic orbitals of appropriate symmetry and energy, the more they will be interacting with each other, and hence will be getting a more stabilized bonding molecular orbital, which will be then formed. It means that the difference in electronegativity between the two atoms increases, the stabilization provided by the covalent bonding decreases, and the polarity of the bond increases if the distance in the energy of the orbitals is sufficiently large. Then covalent bonding will not stabilize the interaction of the atoms. In that situation, the less electronegative atom will lose an electron to the more electronegative atom, and the two ions will be formed. From the figure 1, it can be seen that when the difference in electronegativity is less than 0.5, the bond is mostly covalent. Is moved towards the more polarity takes place when the delta chi value is in between 0.5 to 2, which is considered as a polar covalent bond. But when the value of delta chi increases with that of 2, the bond totally becomes ionic in nature. Now we will be taking a homonuclear diatomic molecule, which is very simple, that is the H2 molecule. For the formation of a diatomic linear H2 molecule, each hydrogen atom has only one s orbital. So, to obtain molecular orbitals for the hydrogen molecule, we must make linear combinations of these two 1s orbitals. The first consideration is when we consider the addition of two 1s functions with the same phase. This produces an MO around both the hydrogen atoms, which are same phase everywhere and are symmetrical about the HH axis. This is known as the bonding molecular orbital and is given a sigma label because of its symmetry. The overlap has been suggested in figure 2, which give rise to a sigma molecular orbital. The next consideration is if we consider that both the combining 1s functions are out of phase. This produces a molecular orbital over the node between the atoms, which is also symmetrical about the HH axis. This is known as an antibonding molecular orbital and is given a sigma star label because of its symmetry. The star indicates the antibonding level. The out of phase overlapping decreases the amount of electron density between the two nuclei. This is shown in figure 3, where we can see that the out of phase addition of the two atomic orbitals is taking place, giving rise to a nodal plane. The increase of electron density between the nuclei from the in-phase overlap reduces the amount of repulsion between the positive charges. This means that a bonding molecular orbital will be lower in energy and more stable than the corresponding antibonding molecular orbital. On this basis, the molecular orbital diagram can now be constructed for the H2 molecule. To clearly identify the symmetry, the different MOs, we add the appropriate subscript G, that is symmetric with respect to the inversion center, and U, which is antisymmetric with respect to the inversion center. The labels are added to each MO. The electrons are then added the MO diagram using the off-form principle, and this has been shown in figure 4, where we have shown a molecular orbital diagram of a H2 molecule. Now we'll converge ourselves to the various principles of the ligand field theory. In coordination chemistry, the ligand is a Lewis base, which means that a ligand is able to donate a pair of electrons to form a covalent bond. The metal is a Lewis acid, which means it has an empty orbital that can accept a pair of electrons from a Lewis base to form a covalent bond. This bonding is sometimes called a coordinate covalent type of bonding, and the bond is relatively called coordinate covalent bond. Or it can also be said as a dative bond to indicate that both the electrons in the bond comes from a ligand. A more specified description of the bonding in the coordination complexes is given by ligand field theory. Essentially, ligand field theory is able to give an understanding of the true origins of the splitting parameter represented by the value of delta naught and spectrochemical series by taking into account the roles of sigma and pi donating bonding ligands in transition metal chemistry. In principle of ligand field theory are similar to those for the molecular orbital theory. These are: first, one or more orbitals in the ligand overlap with one or more atomic orbitals in the metal. Second, if the metal and the ligand based orbitals have similar energies and compatible symmetry, a net interaction will exist. Third, the net interaction produces a new set of orbitals, one bonding and other antibonding in nature. A star basically indicates that the orbital we are talking about is antibonding in nature. Fourth, when there is no net interaction between the atom and the orbitals, then the molecular orbitals are unaffected and are non-bonding in nature as regard the metal-ligand interaction. Fifth, the bonding and the non-bonding orbitals are of sigma or pi character, depending upon whether the bonding and the antibonding interaction lies along the line connecting the metal and the ligand. It can also a delta bonding if it's possible, which is a very unusual type of bonding and is relatively weak. The sigma bonding interaction always involves the ligand acting as a Lewis base and a metal as a Lewis acid. The pi bonding may involve donation of electrons from the ligand to the metal or donation of the electrons from the metal to the ligand, which is also known as pi back bonding. Again, we'll be discussing the molecular orbital theory of the octahedral complexes in terms of various molecular orbitals. Considering ligand, in the formation of a transition metal complex, there is required a central metal atom or ion and the surrounding ligands. The geometry and nature of the complex then depends upon the type of metal as well as the ligand which are surrounding it. The ligand in this context can be of various types. It can be a sigma donor ligand, it can be a pi donor, or it can be both a sigma as well as pi. We can have another category which is a pi acceptor type of ligands. Now we'll be considering only the sigma bonding characteristics of the orbitals. In the octahedral arrangement of the ligands, in order to draw the molecular orbital diagram, we must first generate the symmetry adapted linear combinations of the ligand donor orbitals. Table 1 represents the character table of the octahedral symmetry. Considering only the s orbitals on the ligands, there are a total of 6 orbitals, and in an octahedral symmetry environment, they transform as A1G plus EG plus T1U, as can be seen from the character table. The metal orbitals to be considered are d orbitals, s orbitals and p orbitals. From the character table shown in table 1, it can be seen that the A1G group of orbitals have the same symmetry as that of S orbital on the central atom. The T1G group of orbitals have the same symmetry as the p orbitals on the central atom. The EG group of orbitals have the same symmetry as the dz square and dx square y square orbitals on the metal atom. Since the ligands don't have a combining symmetry with that of 2Tg orbitals, we can say the dxy, dyz and dxy orbitals on the metal atom will remain non-bonding when we will be only considering a sigma bond. This is figure 5 showing the metal atomic orbitals s, px, py, pz, dx square y square and dz square matched by symmetry with ligand group orbitals for an octahedral complex bearing only the sigma bonding. Considering an octahedral complex in which all the 6 ligands have a single valence orbital of sigma symmetry directed towards the central metal atom. Such ligands are called sigma donor ligands and can be neutral, for example ammonia NH3, or it can be charged, for example F negative fluoride. In a strictly octahedral environment, the metal orbitals divided by the symmetry into 4 sets which are given labels that describe their symmetry and multiplicity. This has been shown in table 2. These symmetry labels are also known as Mulliken symbols that are used to describe the set of orbitals in a complex which can only interact with the ligand set of orbitals that are described by the same label. Molecular orbitals for the resulting complex can now be formed by combining symmetry adapted linear combinations and metal orbitals of the same symmetry type. Since we have 6 metal orbitals that can be broken down into 3 groups according to their symmetry, that are A1G, T1U and EG orbitals. The 6 ligand salks, that is symmetry adapted linear combinations of the ligands, then combine to give 6 bonding and 6 antibonding molecular orbitals. The metal T2G set remains non-bonding. All this has been shown in figure 6, which represents the molecular orbital diagram for the formation of a generalized complex in an octahedral environment involving sigma interactions only. Here it can be seen the bonding interactions occurring in between the EG sigma and the T1U sigma orbitals. Again, it can be seen that T2G set of orbital is non-bonding, whereas the EG sigma star orbital forms the antibonding set. The gap between the two forms the basis for the delta knot. The MO diagram formed can now be filled with the electrons according to the Aufbau principle, Pauli's exclusion principle and the Hund's rule. The maximum contribution to the molecular orbitals of lowest energy is from the atomic orbitals of the lowest energy, which in most of the cases, particularly those of the period 2 and 3 in the main group, is from the ligand sigma orbitals with energies much lower than those of the metal d orbitals. Thus, the 6 bonding molecular orbitals of the complex formed are mainly ligand based in character. These 6 bonding orbitals can accommodate the 12 electrons provided by the 6 ligand lone pairs. Therefore, the electron provided by the ligands are largely confined to the ligands in the complex. The d electrons of the metal center occupy the lower energy non-bonding T2G set and the higher energy antibonding EG set. Therefore, the metal-based d electrons tend to reside largely on the metal atom. The octahedral ligand field splitting parameter represented by delta naught in this approach is called the Homo-Lumo separation, where the Homo stands for Homo occupied molecular orbitals or the highest occupied molecular orbital. Lumo stands from the lowest unoccupied molecular orbital. It is approximately the splitting of the metal d orbitals caused by the ligands, whereas in CFT, that is crystal field theory, delta naught was purely a metal d orbital separation. Good sigma donor ligands, which are exemplified by CH3- and H- result in strong metal ligand overlap, resulting in the higher value of delta naught. MO diagrams for various octahedral complexes is described under the next heading. In this section, we will discuss the molecular orbital diagrams of various octahedral complexes, the ligands which have strong sigma donor interactions such as NH3, CH3- and H- lead to the increase in the value of delta naught by increasing the gap between the T2G and EG levels. Thus, these ligands leads to the formation of low spin complexes since the value of delta naught is large. Otherwise, the weak field ligands such as Cl negative, Br negative, S2 negative, etc., which have a small sigma donation, leads to the formation of high spin complexes. It is to be worth noting that the ligands having weak sigma donation can have a pi donation as well. Order of Coulomb energies for metal and ligand orbitals is in the order sigma L is less than d orbitals, is less than s orbitals, and is less than the p orbital. The figure 8 shows the molecular orbital diagram for a complex formed by using a weak field ligand, whereas figure 7 depicts the molecular orbital diagram for the formation of a complex by a strong field ligand, suggesting only the sigma interactions. First of all, we will be discussing the molecular orbital diagram formation of cobalt ammonium complex using the ligand group orbital approach. The frontier orbitals are represented with the sigma bonding interactions. On the left hand side are depicted the atomic orbitals in the metal ion, and on the right hand side are depicted the atomic orbitals in the ligand ion. In the center, both the orbitals have been combined together to give the molecular orbitals. The filling of the orbitals have been taking place according to the off-Bohr principle, according to which the electrons should be filled according to their increase in energy levels. It can be seen that since we are taking a strong field ligand such as ammonia, the value of delta naught is high as compared to that in figure 8, where the value of delta naught is quite less. Again, it can be noted down that the dxy, dxz and dyz orbitals are non-bonding molecular orbitals which remain degenerate and as such in energy. The gap between the non-bonding T2G set and the Eg sigma star antibonding set is represented by the value of delta naught. Now, considering the molecular orbital diagram for the formation of cobalt fluoride complex using the ligand group orbital approach, the frontier orbitals involve the bonding molecular interactions only. It can be seen again that the atomic orbitals in the metal are represented on the left and atomic orbitals in the ligand ion are represented on the right. In the center, we are having the molecular orbitals combining these two atomic orbitals. Again, the filling of the orbitals, that is molecular orbitals, is taking place according to the off-Bohr principle. The non-bonding orbitals include the xy, dxz and dyz orbitals. The gap between the T2G and the Eg levels is suggested by the value of delta naught, which in this case will be quite less as compared to the figure 7. This is again of the consequence that since F negative is a weak field ligand, the splitting parameter will be quite less. In the last, we have again discussed the various molecular orbital diagrams of the octahedral complexes where we are only getting a sigma bond. In this context, we have discussed the molecular orbital diagram of cobalt ammonium and cobalt fluoride complex. Since ammonia is a strong field ligand, it can be seen that it affects the value of delta naught. Basically, it increases the value of delta naught since its interaction with the metal orbital is large as compared to F negative, which is a weak field ligand. We have compared the two molecular orbitals and it can be seen that the basic geometry of the molecular orbital diagram is same, but the gap between the two, that is delta naught, increases and decreases depending upon the value of we are getting a weak field ligand or a strong field ligand. Now we'll be discussing some of the highlights of this module. The shortcomings of the crystal field theory gives rise to the ligand field theory. In the case we are talking about crystal field theory, it has various shortcomings since it cannot explain the electronic spectra, the bonding taking place in the molecules. Hence, we have to depart toward the ligand field theory. The ligand field theory incorporates crystal field theory with that of molecular orbital theory, which together combine to give the ligand field theory for a better understanding of the coordination complexes. The main postulates of the molecular orbital theory are well compatible with that of the ligand field theory. In coordination chemistry, the ligand is a Lewis base and metal is a Lewis acid, which means it has an empty orbital that can accept a pair of electrons from the Lewis base to form a covalent bond, which is actually called a coordinate covalent bond. Ligands can be of various types. It can be only of sigma donor type, it can be only of pi donor type, or it can be a sigma as well as a pi donor. In some special cases, the ligands can also be pi acceptor, which hensely interact with the orbitals to enhance the value of delta naught. Symmetry adapted linear combinations of the various atomic orbitals for the ligand molecule is done, from which we are getting a specified molecular orbitals with overlappment with the metal orbitals of the matching symmetry. For a sigma donation only, we can have a 6 metal orbital set that can be broken down into 3 groups according to their symmetry. These are namely A1G, T1U and EU set of orbitals. The 6 ligand SALCS, which combine to form 6 bonding and 6 antibonding molecular orbitals. The metal T2G set remains non-bonding. Octahedral ligand field splitting parameter, represented by the value of delta naught, in this approach is called Homo-Lumo separation or a Homo-Lumo gap. A good sigma donor ligand, for example CH3 negative and H negative, result in strong metal ligand bonding overlap, resulting in the higher value of delta naught. Thank you.